All right, welcome ladies and gentlemen to section 7.2, matrix algebra. So we're not just going to be looking at matrices in general, but we're going to be looking at some of the math involved in matrices. So basically, you guys probably understand that a matrix is just a set of numbers, mainly looking like this. You could have positive numbers, negative numbers. You can have fractions in there. You can have all sorts of things. This is a basic matrix. So let's go ahead and get through all of the little things so we can get into the more complex things relatively quickly. So m and n are going to be positive integers. They can't be negative because that wouldn't make sense because they describe the size of the matrix. So we say a matrix is an m by n matrix. It's a rectangular array. Array is just a group of things, a list of things. And it's m rows. This is very important. M rows by n columns. So this particular matrix up here that I said, rows go left and right, columns go up and down. Hopefully you knew that already. This is a 2 by 3 matrix. Here's an example of a very large matrix. Sorry, it's pixelated. Found a bad version of this picture, but this is an m times n. What we do here is we can indicate each individual element of this matrix by giving it little subscripts. So A11, or this thing I'm going to mention here, A11 means row 1, column 1. So if you go down to A23, this A23 represents going down to row 2, column 3. Hey, there's A23. So I said, okay, what is M4? I would go down to row M and be the 4th column over, whatever value is in there. Or if up here I said A13, so a row 1, column 3 is going to equal to 3. All right, pretty straightforward, but some little things that you need to know. We don't use this a whole lot, but just so we can kind of use the same terminology, m times n, or not m times n, m by n is the order of the matrix. So this is the matrix that I have up here at the top is a 2 by 3. The order is 2 by 3. All right. These three concepts right here are usually the ones that we cover in Algebra 2. They're very, very straightforward. For addition and subtraction, matrices must be of the same order. You can only add, if you had a 2 by 2 matrix, you can only add to it a 2 by 2 matrix. Oops, no comma. You cannot add anything else because when you add or subtract, you add and subtract corresponding entries. So here I'd say 2 plus 6 is 8. That would be row 1, column 1. Row 1, column 1 becomes row 1, column 1. 1 plus 1 is 2. 6 plus 0 is 6. And negative 1 and 1 make 0. So this would be my sum matrix. You can do that with differences as well, subtraction, same idea. So this statement here, sum and difference matrix is of the same order. So I started with 2 by 2, I added a 2 by 2, I end with a 2 by 2. For scalar multiplication, scale multiplication just means taking a number and making the matrix bigger or smaller, but not the order. That's not what I mean. And it's basically scaling things up or scaling them down. It's just multiply each entry of the matrix by the particular scalar. So I would look like this. 3 times the matrix, 1, 7, 2, and a third. I would just multiply each entry. So this would become 3, 21, 6, and 1. That's very simple. This particular slide here is a very simple concepts here. The additive identity. Well, in basic algebra, when I say 1 plus what equals 1, that what has to be 0 because 0 is what we call the additive identity. If we add it to something, it doesn't change its value. So it's the same thing here. It's just called the zero matrix. It's where all the entries are 0. So if I had a 2 by 2, this would look like this. Very, very simple. That's the zero matrix. It's called the additive identity for a 2 by 2 matrix. Additive inverses are the same as here. If I said 1 plus what equals 0, it's two things that add together to get the additive identity. And it's just going to be the opposite. So it's two matrices whose sum is the zero matrix. So an example would be something like this. 1, 2, 3, 4. If I added that to -1, -2, -3, -4, that would create a zero matrix. So these two matrices are inverses. Or sorry, they're additive inverses. They're not inverses of each other. Additive inverses. All right, now we're going to start ramping this up a little bit. Matrix multiplication. Not always is this something we cover in Algebra 2. So let's take a look at what this is going to look like. If you have two different matrices, we usually use capital letter A, B, C, D, E, F. That's what your calculator is going to use. If you have an M by R and an R by N matrix, and you multiplied them, your result is an M by N. Notice the R's here are the same. That's very important. The columns of the first have to be the same as the number of rows in the second. And you might notice in this case, I can do A times B, but I couldn't do B times A. There's very kind of cool little things with matrix multiplications here. So an example, if I was to do matrix A, which is a 2 by 3, and matrix B is a 3 by 4, I look at this and I go, hey, this 3 matches with this 3, which means this 2 and this 4 is going to be my result, the size. So because the 3's match, it's possible to find the multiplication. If they don't match, it's not possible. So if I tried to do, I could do a B. But if I tried to do BA, that would be a 3 by 4 and a 2 by 3. Because the 4 and the 2 don't match, I can't do it. So let's look at how to do this. I'm going to put this up here and I'll explain what it means as I kind of look at an example. If I was to have the matrix that was 1, 2, 3, 4, 5, 6 times, because this is a 2 by 3, obviously this gets a little bit bigger. Let's see, let's go 0, 1, 2, 4, -1. It doesn't really matter. So if I create this, I have a 2 by 3 and a 3 by 4. My result, oh my goodness. Get back here. There we go. My result matrix is going to be a 2, my fault, not paying attention to myself, a 2 by 4 matrix. So I'm going to have 2 rows and 4 columns. And what this represents over here on the left, the multiplication matrix here, the AB, the first entry, the row 1, column 1, is basically row 1 times column 1. So 1 times 0. So essentially here for this first one, so AB of 1, 1 is equal to 1 times 0 plus 2 times -1 plus 3 times 3. If I do this, this is 9 minus 2, which is 7. So the 7 goes in this entry. It doesn't matter the order you do this. If I was to go, hey, what is A, B, 2, 1? So I take row 2 and multiply by column 1. So I get 4 times 0 plus 5 times -1 plus 6 times 3. So I get 18 minus 5 is 13. And then I just continue this process. For this one here, this is row 1, column 2, or sorry, row 1, column 2. So I do row 1 times column 2. So I get 1, 12, and 3 when I do multiplication. 1 times 1, 2 times 6, 3 times 1. So 4 is 10. And I just continue this process for all 8 entries. Row 1 times column 1, row 1 times column 2, and then I just continue. All right? Save a little bit of time. Maybe you should fill that out yourself. Maybe you can get the right answer, hopefully. Okay, multiplicative inverses. So you can only have, there's a lot of things that we can only do with square matrices. So like a 2 by 2 or a 3 by 3 or a 4 by 4. There's some things that we cannot do if they're rectangular matrices. If you took 2 square matrices and their product was what we call the identity matrix, then they are called inverses of one another. And the identity matrix is a matrix where ones are on the main diagonal and the rest of the matrix is filled in with zeros. So for a 2 by 2, it would look like this. Ones are on the main column, main diagonal, and zeros fill in the rest. This, I'm going to mention here, is denoted I sub 2 because it's the identity matrix for a 2 by 2. If I was to do I3, the identity matrix for a 3 by 3, I would have ones along this column or this diagonal and zeros that fill in the rest. And this continues for all sizes. I4 would have 4 ones and then a whole bunch of zeros that fill it in. And one of the things that we like to do is actually figure out some inverses of matrices. But there's a lot of stuff to go before we can do that. If they multiply together to get the identity matrix, it tells you that B is equal to A inverse, or B is equal to the inverse of A, or A inverse. And this -1, again, does not mean the reciprocal. This does not mean 1 over A. It means the inverse of A, and we're actually going to use that button on our calculator later. But what you do need to notice, and you'll find out, not all square matrices have inverses. Some of them just don't. If your square matrix has an inverse, we call it non-singular. These are just terminologies that get used in the textbook. We got to know. And if it does not have an inverse, it's called singular. And then lastly here, a square matrix has an inverse if and only if the determinant is not equal to 0. Well, it'd probably be a good idea if we knew what the determinant was, huh? Pretty sure that's the next page. Okay, so we need to know this definition. If the determinant is 0, then it has no inverse. So let's figure out how to find the determinant. Determinants are actually a very simple process. They get a little bit more complex the larger your matrix becomes. But in a 2 by 2 matrix, it's simply take this column, this diagonal, multiply those two numbers. This is for 2 by 2, by the way. So A1 times A22, A11 times A22, and subtract the product of that diagonal. Please pay attention to this notation, the bars, almost like absolute value. So if I said matrix A was 1, 2, 3, 4, and I said find the determinant of A, we could write this as the determinant like this, 1, 2, 3, 4. which is equal to 1 times 4, the main diagonal, minus the not main diagonal, 2 times 3, so we get 4 minus 6, which is negative 2, which would actually indicate, because this is not 0, A actually has an inverse. We'll find it later. A has an inverse. For a 3 by 3 matrix, this is kind of a cool formula. There's a different way to do this, but I'm going to try to stick with this particular method. What this says, if you have a 3 by 3 matrix, you're going to take A11 and you are going to multiply by the determinant of these 4 pieces. Basically meaning, I'm going to take this value 1, 1, and I'm going to scratch out this row and scratch out this column and be left with a 2 by 2. So it's A11 times the determinant of that little 2 by 2 matrix. Then it's minus the next one going down this column here. I cross out this row and this column, and I'm left with A12 and A13 with the A32 and the A33. So I'm finding the determinant of that little matrix. And then I'm going to add. So notice it's plus, minus, plus. That's important. And then you do it for the third thing in the same column. You find that. You find your determinant of a 3 by 3. If I did a quick example here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Takes a little bit of work. However, it's not impossible. I would take the number 1 and multiply it by the determinant of 5, 6, 8, 9. Oops. And I would subtract. So I did the 1. Now I'm going to go to 4. I would subtract 4 times, if I cross that row, that column, I would determine it of 2, 3, 8, 9. And then I would add 7 times the determinant of 2, 3, 5, 6. And then determinants are numbers. So you're going to get a number for your answer if it asks for a determinant. I'm not going to finish this problem because I think it's pretty self-explanatory to get, okay, here's a number times 1 minus 4 times a number plus 7 times a number. You get a number as your answer. Determinants are very, very important in the study of matrices, by the way. Okay, now you should crack your knuckles and you should get ready for the good stuff. Well, a 2 by 2 is not that bad, actually. If I want to find the inverse of a 2 by 2 matrix, what I want to point out here is the inverse of a 2 by 2 matrix. If you're given A, B, C, D, it's 1 over this kind of, where'd this come from? Well, it's AD minus BC. So this is actually 1 over the determinant times matrix A, or actually a variation of matrix A. What we do is we swap A and D and make the other two negative. So for us, that's basically what we're doing. We're swapping A and D, and we're making the two other ones negative. Or opposites, right? Not making them negative because you're making the opposites. So if you look at the example that was given here, the matrix 2, 3, 1, 2. You can do it this way if you'd like, if you kind of just pick out the pieces A, B, C, and D. But if we look at this, just what's the determinant of matrix A? Well, the determinant is 4 minus 3, which is 1. So here I get 1 over the determinant, which was 1, times the matrix. Well, I swap A and D. Well, in this case, they're both 2s. And I make opposite of the other two values. And then I multiply this number in, and notice that we get 2, -3, -1, 2. So this matrix right here is equal to, as you see over here, A inverse. Oops. I know I said this before, but I'm making sure it's at least more than one place in your notes. A square matrix has an inverse only if the determinant is not 0. Notice the determinant here was 1, so it was not a big deal for us. What about a 3 by 3? A 3 by 3 is where now you really should crack the knuckles, take a deep breath, and hold on tight. So there's something that you need to do first. This is called creating what's called a matrix of minors. At least some places it's called that. I tried. Some people just don't call it that. Whatever. What we do is we take the 3 by 3 matrix. So let's kind of take a 3 by 3 matrix, and let's go 1 0 1 2 2 1 3 0 1 0. Yeah, make the numbers small so we can kind of do it quicker. So what we have to do is we have to make this matrix of minors. So row 1, the value in row 1, column 1, is replaced with the determinant after we cross out row 1 and column 1. So the determinant here is 1 times 0 minus 3 times 1. Which is 0 minus 3, so -3. Then you continue and you say, all right, let's go into the second one. So I'm going to look at this second one. I'm going to cross out row and column, and I'm going to be left with 2 times 0 minus 3 times 0, so I get the value of 0. All right, then I continue. I probably wouldn't cross things out all the time if I were you, because things are going to get kind of messy. And I go, okay, oops. Come on, give me a pen. I cross out the next row. And 2 times 1 times 1 times 0, or minus 1 times 0 is 2. And then you continue this process down, and you go, okay, once you get the hang of it, you don't need to cross these things out anymore. And I go, okay, let's go to column or row 2. Cross, cross. 1 times 0, 2 times 1, so -2. Middle, cross out middle, middle. I get 0 times 0 minus 2 times 0. So it's 0. That's nice. This row, this column, 0 minus 0, that's 0 too. Okay, good. Row and column, I get 3 minus 2, which is 1. For row 3, column 2, row 3, column 2, I get 0 minus 4, which is -4. And lastly, I get 0 minus 2 is -2. And once you get the hang of this, this actually goes pretty quick. That is not the inverse, however. That is just the matrix of minors. Okay, I told you, take a deep breath and hold on tight. So there's more to go. There's more to come. Oh, then we got to make another matrix. We have to create what's called the cofactor matrix. So cofactor just means go into your matrix and change your signs if necessary. So you have the matrix in front of you. I hope you wrote it down anyway. And so I'll write it up here again, hopefully, wherever I can find some room. I had -3 0 2. I have -2 0 0. And I have 1 -4 -2. The cofactor matrix says change these to pluses and minuses, or where it says plus, it means keep the sign. Where it says minus, it says change the sign, basically. So I'm going to say it's -3, -0, but that doesn't make sense. 2, +2, because I got to change the sign. 0, 0, 1, +4, and -2. Okay, so that's the cofactor matrix. That's not the inverse. Okay. Then we have to do something called the transposition. So we have to transpose the cofactor matrix, and this actually doesn't take much work. But what it happens is row 1 becomes column 1, and row 2 becomes column 2, and row 3 becomes column 3. And this is called the transposition. So we started with matrix A, which I forgot to write down outside of the notes here. So I started with A. I created the matrix of minors. So I went like this. I went made matrix of minors. Then I went down to here and I made the cofactor matrix. Then I have to transpose. So AT is equal to the transposition. In this particular case, I'm not sure if we should have called it A, because A is not actually the original. We're not working with A anymore. But the transposed matrix is now row 1 becomes column 1, so -3, 0, 2. Row 2 becomes column 2, so 2, 0, 0. Row 3 becomes column 3, so 1, 4, -2. That's pretty simple. But that's still not the inverse yet. So I'm writing this down so I don't forget it. Hold on tight, we're almost done. Now we can actually calculate. Now that you have that transposed matrix, you can multiply by the reciprocal of the determinant of the original matrix to the transposed cofactor matrix. And then, of course, this me being dorky wasn't that fun. Okay. So you find the original determinant of A. So you find the determinant of A, 1 divided by the determinant times that -3, 2, 1, 0, 0, 4, 2, 0, -2. And that is going to equal A inverse. But because I forgot to write down my matrix A, I can't find the inverse because I don't remember what the matrix was. Hopefully the determinant wasn't 0. If the determinant was 0, we went through a lot of work that wasn't necessary. That's why we should find the determinant first. Okay, that was fun. What else can we do that's going to be fun? I know some of you just said stop the video, but that's not fun. That's, I don't know what that is. Lazy. The largest thing that I think I'm going to have you guys do by hand is to find the determinant of a 4x4 matrix. But it follows the same process as finding the determinant of a 3x3 matrix. You can choose any row or column. There are better choices than others. Usually small numbers and zeros are pretty nice to use. Zeros are extremely nice because it gets rid of like parts of your calculations. From that row or column, what you end up doing is basically the same thing you did for a 3x3. You take that first term and you multiply it by the determinant of the leftover 3x3. So we get a 4x4 matrix here. Let's do 0, 1, 0, 2, 3, 0, 1, -1, 4, 6, 5, 3, 0, 1, 1, 1. And like I said, any row, any column, doesn't matter. Choose a good one. I would not choose this one. I would not choose the row with 4, 6, 5, 3 because that creates a lot more problems, or bigger numbers, I guess. So we're finding the determinant, so I shouldn't have done these bars like that. I should have done straight bars. But I kind of like the row with 2 zeros and small numbers. You could like this one too with just the ones. Either way, you should get the same answer. So let's choose, I'm going to choose row 1 since that's kind of what I set up here. So I need to take the first value, that row 1, column 1, and I need to multiply by the determinant of the leftover 3 by 3 after crossing that row and crossing that column. So I'm left with the determinant of 0, 1, negative 1, 6, 5, 3, 1, 1, 1. And then I'm going to, notice I'm going to subtract 1 times the next determinant. So cross out row 1, column 2, and I get 3, 1, negative 1, 4, 5, 3, 0, 1, 1. Boom. Then I'm going to add 0 times this leftover 3 by 3, 3, 0, negative 1, 4, 6, 3, 0, 1, 1. And then I'm going to subtract 2 times the leftover 3 by 3's determinant. 3, 0, 1, 4, 6, 5, 0, 1, 1. Oops. Well, you got to remember the finding a 3 by 3 matrix, determinant of 3 by 3 matrix is also does the same kind of thing. But notice here, the zeros actually cancel this out and they cancel this out. So you're only left with these two things to do. Okay, I will not make you find the inverse of a 4 by 4 matrix by hand. What I do have here is actually how to do it on a calculator. What you'll notice on the assignment sheet, however, is you must do them by hand. I know whether or not you did them by hand because it's going to take more than just 5 lines for all of your problems. You must do these things by hand, but you do have the ability to check your answers with your calculator. So on either the 83 or the 84, I know I said yellow, and I think that's more on the 83, except for it's just the second button. You need to find the matrix button. If you go in to choose, you need to go in and choose edit. Just choose any random matrix, change its size, and it gives you little options for rows times columns. Fill in the entries to your matrix. If you have taken chemistry or anything where you had to do regression lines and all that sort of stuff, it's very important that you pay attention to your accuracy. If you were supposed to write in a -2 where it was where you wrote in a 2, things are going to come out wrong. So be careful. Then you quit, and then you go back and you choose a matrix. And you can do all sorts of stuff. They have math where you can do determinant. You could do the inverse. All you have to do is choose the matrix and go to the -1 button on your calculator. All right. That is that. Now, for those of you that actually watched to the end of the video, I'm going to give you a little trick for a 3 by 3 matrix. So this will help people that have done 3 by that actually pay attention to the very, very end. So 3 by 3 determinants. There is actually a trick to this. If you had the matrix, let's call it 1, 2, 3, 4, 5, 6, 1, 1, 1, just to keep the math a little bit easier. And you wanted to find the determinant of that matrix. What you can do is you can go 1, 2, 3, 4, 5, 6, 1, 1, 1. And rather than doing that whole process, you can actually do a little trick. Take this row 1 and tack it over here, and take column 1, and then column 2 and tack it over here. And then what you can do is you take all 3 of these diagonals, just like you did in a 2 by 2. And you find those products, and you say, okay, 1 times 5 times 1 plus 2 times 6 times 1 plus 3 times 4 times 1. So I get 5 plus 12 plus 12. And then I'm going to go here, and I'm going to take the other 3 diagonals. Just like I did in a 2x2, and I'm going to subtract 5 times 3 times 1 plus 1 times 6 times 1, plus 4 times 2 times 1, and I'm going to subtract 15 plus 6 plus 8. And I get, here's 24, and 5 makes 29, minus 20. Oh, look at that. Couldn't have chosen that any better. And I get a determinant of 0, which technically means that has no inverse. So this is a benefit for those of you guys that actually paid attention to the from beginning to end. I know some people stopped the video, so kudos to you for going all the way to the last second. You realize, oh, there's some extra time on the video. I wonder what he said. All right, I will see you guys tomorrow. I hope you hung in there. Tried to keep this as short as possible. And let's tackle those matrices tomorrow.